in the internet. Welcome to our 4th edition of the Rust Munich Meetup this year. Today we have some exciting talks. One is about the profiling of async applications by Vitaly. We'll see it in a bit. And then the second talk after the break is ensuring memory safety for the transition from C or C++ to Rust by Oliver. That is brand new research stuff that we're going to look at. So very excited. And yeah, so today we are here at SAP Signavio, and that's our sponsor for today and also my employer. And yeah, I wanted to give a very brief overview how we are dealing with Rust, or what we are doing with Rust. And yeah, I try to keep it very brief. And for this, we have a few slides. And let's see. So one second. Now, all right, let's go. Okay, let's start with this. SAP. When I joined SAP, I had no clue about what SAP is doing in the open source area, which for me is kind of very important. And so I learned about this. And so I wanted just to share with you a couple of facts. Because already since 1998, there's something going on, right? And then it just increased over time. And SAP joined the Eclipse Foundation in 2004, for example. Not that Eclipse Foundation matters to us Rust stations, right? However, there are so many interesting things going on that I was very surprised and impressed. So that is a quite significant contributions over the years. And then one more, facts and figures, also learned about that. So if you look at GitHub open source projects contributions, SAP is among the top 10. It's the last, but the top 10, right? So that is, for me, that's also kind of very impressive to see all these areas where SAP makes contributions. And yeah, there are so many projects going on. So really, I mean, every year I can just continue to learn something new. It's pretty big. So here again, the foundations where SAP has some stakes in, and yeah, also the Apache Software Foundation, which is interesting. But now let's come to SAP Signavio, right? So Signavio was a startup that got acquired by SAP. I don't know, roughly 2 years ago or something. It's Berlin-based, and what it is basically, it's a cloud-based process transformation suite. Yeah, that sounds pretty big. So it's a SaaS application that can be fed with data from whatever systems. It does not need to be SAP, it can be whatever. And then, you can analyze your data, roughly said, right? There's so many functionalities. So here you see basically all the things that are in this SaaS software. And what I want to tell you today is about the SAP Signavio Process Intelligence, which is focused on process mining things like business process mining and yeah, analysis in depth, right? And there we have those two things. Basically, an own language, which is similar to SQL. It's called Signal, stands for SAP Signavio Analytics Language. And we have automated insights. Those two things are basically Rust powered at SAP Signavio. Yeah, so Signal, SQL, yeah, maybe, I don't know. So this is how it looks in the web UI, basically. There you can define widgets that helps you to get a better understanding of your data. And those widgets, they accept, for instance, arbitrary signal queries. And as you can see, it looks very, very familiar like SQL, but it operates on like nested data. So this is not like flat tables or something. It's kind of a like a language for business processes. So we have business cases, and in those cases you have events, right? And this is the nested structure that you can analyze. And so you get a nice understanding about whatever question you want to answer about your business data. And the other portion is insights. That's called process insights or automated insights. So basically you get those nice and shiny graphs that getting calculated based on like statistical algorithms that we in our team implement. And then from there you can, you know, drill down and get a better understanding what's going on in your business processes. That was very brief. So yeah, to summarize it, these are the two products, and we use Rust and basically Rust only. And everyone is really happy with, you know, the performance, the language, and every, like all the assets that we get with it. So gives us really confidence to release fast and not break things. So yeah. And for the rest, I would say enjoy our nice talks that will come now, and handing over to Vitaly. Not quite? Sorry. We have to switch slides. 1 second. We want, just a second. We want to thank our other sponsor, TechnoSearch. Basically, they provide us with the equipment like the microphones today. It's basically search companies for engineers, basically. Cryptography, hardware, blockchain, backend development. Yeah, whatever you need, basically you can approach them and they will help you finding the right people. Excuse me? You can find him. No one is here today, so unfortunately. But you can find it on the web and reach out to them and just, you know, mention you coming from the Rust Meetup, and they will know what you want and what you talk about. All right. So with this, handing over to Vitaly.
Okay, thank you. Okay, is it streamed, right? Okay, great. Yep. So, hi, folks. My name is Vitaly Bragilevsky. I work at JetBrains as a developer advocate, and like part of like one half of my job is connected to our Rust stuff. So we have a team doing IntelliJ Rust plugins. So like half of my time I work with them, and another half of my time I work with Fleet IDE. And it turned out that this week our Rust team has a gathering here in Munich. So for the whole week, the whole team is here in our Munich office. And when I saw this information about this meetup organized, I was just happy. So it's a great chance for me to connect with you folks interested in Rust here in Munich. So I decided to apply. So here am I. So this is like a preliminary, a little bit drafty version of my talk at RustConf next week in Albuquerque. So it's not precisely that talk. So I tweaked it a little bit, but so it's in some sense it's special. And yeah, so yeah, here am I. And you may know that CLion is our primary tool for doing Rust development. Of course, we have IntelliJ Rust plugin, and it works in IntelliJ IDEA, Community Edition, and PyCharm, and other IDEs. But CLion is our flagship product for Rust developers because it features the most powerful support for Rust development. Okay, so let's get to profiling. So here you can see the results of our yearly survey of state of developer ecosystem survey. It's not only for us developers, and it's not only for the users of our plugin. So like half of the survey participants actually mentioned that they work with VS Code and Rust Analyzer. So it's not just our customers. It's just more broad audience for this report. And if you look at this particular question, we ask it every year, and results don't change from year to year. They're mostly the same. So when we ask what profiling tools do you use for Rust, the huge majority of folks answer that they don't use profiling tools at all. And only 15% say that they use profiler bundled with IDE. So we don't mention which IDE. So that's the answer. So that may be something, some tool, some extension for VS Code, for example, doesn't matter. So for us as an IDE company, these results are, well, we'd like to have this answer, answering more folks answering that. And all other numbers, they're really small. We can see macOS folks use dtrace mainly, Linux folks use perf, but numbers are really small. And we see some problem with this. So why don't we, as Rust developers, why don't we profile our code? And usually, folks mention several excuses or reasons why they don't profile. Reason number one or excuse number one, well, it's hard. If you look any tutorial on profiling, you will see that it is really, really hard. So there are hundreds of command line options. If you look at the documentation for perf, it's just mind-blowing. It's really very hard. Excuse number sorry. Excuse number one is that, well, at this time, it's not necessary. Folks will say, well, it works. The performance is quite good. We don't need to profile it. It just works. We're not bothered with all that stuff. And excuse number three, which I quite often hear, well, there are some very smart folks in our team, and they profile everything for us. We don't need that. So we shouldn't say that everybody should profile their code because there are those smart guys. And this is the reason that I don't like at all. Really, I think that that's a wrong reason, wrong excuse for not profiling things. So I believe that we should profile it. And there are many reasons why we should actually profile our code. And for me, reason number one is that, well, we like to claim that Rust programs are fast, very performant. We are better than every other programming language out there. But we should actually prove that every single time. So it's not enough to claim things like that. So in order to prove that, we have to profile. We have to make sure that everything really performant. So also, if we look at other ecosystems, we'll see that they have much better tooling for profiling, much more powerful. like Java or .NET, we could say, well, it's managed code and it's easier for them to implement profiling tools. Well, maybe that's the reason. But for C, C++, for Go programming language, profiling tools are much more powerful. And when I say powerful, that means that it's easy to achieve very good stuff from those tools. And that's not the case for Rust at the moment. And the problem is that we could get better tooling if we have wider usage of those tools. Like if there are like 100 folks in this world using perf professionally, then perf will never be better because there is no enough demand for making it better, actually. And that is the same stuff with our tools from JetBrains. If we see that our customers don't use this particular tool, maybe we don't need to invest any effort into making it better because, well, folks don't use it. But there is this idea, this Pareto rule, 80 to 20, like to achieve 80% of outcomes, you just need 20% of effort. I believe that in Rust profiling, we have very close situation. Like for 99%, in my opinion, successful outcomes for profiling, we just need only 1% of those tools. We just need 1% of functionality of those tools. So we don't have to be experts in profiling Rust code in order to get successful results of profiling, in order to understand what's going on wrong with our code. So that's an idea. So we don't have to be experts. We just can start profiling without too much effort, and we can be successful in that profiling. The main method which we use normally for profiling that's most powerful is so-called sampling profiling. And the idea is very simple. Like we have running program, we pause it many times a second, like 1,000 times every second, and explore stack traces. So that means like we are taking samples, so we look at them. And then we combine samples by functions, like this function took like 10 samples, and we compute the total time. And it's not time in terms of seconds usually. It times in terms of those samples. But we know that we have regular number of samples every second, so we can compute time somehow. And of course, best way to present that stuff is flame graphs. So very well-known tool. It is very simple. There are some variations, but that's the main thing for profiling, for presenting results of sampling profiling. So let's look at an example, very simple one. We want to fetch an HTML page from web. And I will show you several examples using several crates. Like this one, very simple, is UREC library. So what we are doing here, it just, we issue a request. There's some locator somewhere, so we do get, and then we actually issue that call, and then we transform everything into string. And for me, result is just length. So we don't try to print it, nothing like that. Just we're interested in the size of the HTML page that we're getting. And so we have this code, we have main function, which basically just calls just this function and nothing else. And we run profiling. Like in C-line, it's very easy. Just you have this button to profile code, and you may get something like this. And if you use, for example, Cargo flame graph, you will get the same result, like in many cases. And if you look here, you will see something which is, well, doesn't look like something done right. So this is a program which runs very quickly. And you will see here like 3 samples. So our programs use many functions. And here you can see just basically 3 stack traces. So sample number 1, sample number 2, sample number 3. That's it. So it's not very informative. And it's not the real result of profiling. So something is wrong. So this very first problem which you may face when you use profiler is just you get something and you believe that this is true. Well, it's not true. And the problem here is because this program is it is too performant. Like, so profiler does not have enough information for that. So the problem, if we try to find some functions, like there are no like half of functions which are actually executed here, we don't see it here. So we can try differently. So we can try like run it next time, like in a second or so, and we'll get completely different result. Like basically I did that. So I ran profile first time, then I run profile second time, no changes in like configurations, nothing. And I'll get totally different result. If you do that and you see that you get different results, that basically means that something is wrong. So it depends, like if you are lucky, you get a lot of information. Like here, you see many samples. If you are not lucky, you just don't get this information. So if you base your like decisions on what to do with the code, if you base it on this like wrong result, well, you have a problem. You just don't actually get what's going on here. So one advice here is to tweak so-called sampling frequency. Like these are default values in Selenium, like about 1,000 samples per second. You can write 2,000. You can write 3,000. More than 3,000 is not recommended because it's not your program anymore. It's not your code. It's mainly like what operating system is doing and not your code. But so this default is quite good actually. We'll see other ways to do that. But if we like make it twice bigger, 2,000, the result will be like this one. And we'll see that our function, like urec fetch, the only function in main, takes only about 60% of the whole computation. And when you have this profiler results, so you can see here is all our program, like the whole slide. And I focused on some small part of it because everything else is not our program. Like here, there is some machinery from Rust programming language loading our main function. Here we have some dynamic libraries like Core Foundation, like I did that on macOS, so it's some artifacts of running this program and macOS. So we're not interested in that. So if we have a good tool, we can just focus on what matters here, and we try to analyze. And we can see that, well, we are connecting to socket, and this connection time is the longest here. So most of the time you spend on connecting to something, and then you analyze your response here, small time, like preparing your request. So you look at the results and see what's going on. All right, that was my first example with urec library. Let's try to do some curl. Like there is a curl Rust crate for fetching web pages with the curl library. So this is my function. They call it like easy interface for curl. And here, basically what we're doing, we are preparing to use that interface. Body, this will be our result. So we provide some URL. And then what we do, actually, we use this transfer method to provide special function which consumes results from profiling. So curl is trying to be very efficient. So it's not going to provide us with the whole result. We have to accumulate it by ourselves. So for example, here we are just using string concatenation to come up with a full result. By the way, do you have any issues with this code? So this function here, this closure, will be called several times depending on the actual size of the page. So we are concatenating it, and then we actually start performing this request. So this is where all the job is done. So these are preparations. So do you see any issues here, by the way?
I wonder what's happening with the result of the closure, maybe? The data length?
I think it returns just total number of bytes read from the stream. Yeah. Okay, I will show you another version. So here we are doing this stuff with strings, and yeah.
I think from UTF-8 can fail.
That.
It can cut at the wrong point.
That's true. That's true. That's not the point here. So that is completely wrong version, because we have to do this from UTF stuff when we have the whole buffer ready for that. That's absolutely true. So whenever we work with strings, we have to be very careful because bytes are not characters in UTF-8. Yeah.
I mean, I don't know how the string implementation works internally, but I could imagine the system is quadratic in the length of the number of appended and how often you append, basically.
Thank you very much. You will see that there are some issues with this idea right after when I show you the next version. So my next version differs in one regard. So I have a buffer here, which is a vector, and I am extending this vector with this buffer with this data which I received here. So, and then I start performing it. And then when I have the whole result, I'm doing from UTF. So this is more correct version here. So do you think, is this version better? Is it more performant or not less performant? So string concatenation and extending buffer. Yes.
Depending on the data amount it gets, that you get back, basically, you have reallocations all over the place.
Mm-hmm.
And those can come costly.
So in my example, the actual page I am fetching is about like 4 kilobytes, something like that. So with this information, can we say which one is better? And it takes actually in both variants, it takes 2 executions for this closure. So like it's larger than one TCP segment. So it takes 2 invocations for this closure, additional information. Okay, so you know what? Like I like that like most of you are silent, because the right answer is that you never know. Like with programming languages these days, you never know what's going on at runtime. So the only way to get the actual information is to profile this code. Well, you can do benchmarking, of course, that's another approach. But profiling is the only way to understand what's really going on at runtime. So we never know. That is very important. Like sometimes in Java, maybe we can have, like in Python, we know that there is some problems with this implementation, so we can do this and that. But here in Rust, you never know what's going on at runtime. So we'll do like some profiling for these 2 examples. And this is my code. So I don't want to increase sampling frequency. I will use like 1000, which is a default value. But instead, I will do 50 calls to both of these functions. That's another approach. It's not always feasible to do that. So if you want to have something more real results, you don't do that. But here, synthetic example, that's fine to run just 50 times both functions and see what's going on. All right, this is our main function here. So we start profiling, and we see that we have like enormous amount of threads here in profiler. And all the threads are actually less than 1% of total time. So a lot of small, I think it's like 100 of threads here for this simple example. And this is a combined view for all the threads. And if you see, we have this curl fetch buffer, this one here, So this is curl fetch buffer. This one here, curl fetch string version here. And all those threads are actually doing get adder info. So they are converting the main name from the URL to some AP address. Like this, like I think it's like 20% of the whole time is about converting like the same address again and again. But curl is doing that using this specific threads here. All right. So we can focus on what really matters here. So I've chosen only one thread, which is doing all the job we need. Like all other stuff is get adder info. And if we look here, we'll see that fetch buff takes like almost half of the whole program. So remember, we had 20% of the program doing get adder info, 50% buffered version, and the rest, so that should be like 30%, maybe 35%, our string version. So in this setting, string version is, well, 1.5 times faster, more efficient. So we have to understand what's going on here. So our job is technically to analyze these parts of this flame graph and see where are the problems. And it turns out that sometimes we just don't know what to do, because the main difference here is this part. My curl connection connect here and there. Like we have almost same implementation. It differs only in our buffer string stuff. Otherwise, it's just the same. But here, this function from somewhere, some dynamic library for curl, so it's not our function. In this example, it takes 15%. In that example, less than 10%. And this is something we don't know what to do with it. So it's just some strange thing in curl implementation. But these results can be used like to go to curl developers and ask them what's going on here. We have the same implementation, same functions, but what's the matter? But at least we've got this information. So this information is enough to go to them and ask what's going on. But sometimes we can look closely to other parts and see that, for example, here we have this curl fetch buff function. And if we look closely, we'll see that we have a lot of vector allocations here. And in this example, this is the main reason why this implementation is slow. So string concatenation is implemented in a little bit better way. Or maybe they have different default values for the size of the buffer they use internally. And for us, we don't do that stuff here. And this version with buffer is slower. So, well, we can do something like that. If we know what amount of data we are expecting, at least like for some sample data, maybe we could have that. So we can reserve this buffer, and then it will be a little bit faster. Not much faster, I should say, but so still that connection stuff is just different in both implementations, but we can make it faster. And it's easy. It's not some magic, some real profiling, like getting some insights about internal implementation. Well, we just know that there is a buffer, there is this extension size, and if we give a little bit more memory, if we reserve for that memory, then we are getting more performant implementation. So that's an idea. Remember, you can get 99% of successful outcomes for profiling by just using 1% of knowledge about profiling. That is very important. Okay, in the title of my talk, I mentioned that I'm talking about async applications. So we want to check what's going on with async applications. Before going there, let's try to look at another library. Like I think this one is one of the most popular crates, which is called request for fetching stuff. And this crate is deeply asynchronous. But they provide this blocking interface, which is very simple. We just say request blocking get, and then we convert everything to text, and that's our result. So it's much easier than curl, for sure. And of course, we like to, like in Rust, which is high-level programming language, we prefer coding in this style. All right. So let's profile, and once again, so the main here is just repeating this function 50 times. So nothing else. So blocking interface for request. Okay, if you profile it, you will see something extremely, extremely strange. So this is my request blocking fetch function, like less than 20%. What is this? Like once again, my main function has only one loop, 50 iterations for that function, and it's less than 20%. Well, this is Tokyo runtime. Tokyo, tower on top of Tokyo, and hyper on top of tower. So all that stuff. And the main problem that we can clearly see here, and our program is not asynchronous. We're using blocking interface for request. But inside that blocking interface, there is all that stuff. And so, well, it's kind of difficult to understand where are the issues, because we don't see it there. Our function is there. We don't know anything about internal Tokyo implementation. But real issues will be here and not there, in that small part. So, well, there are some issues. And like about these issues, if we are doing something asynchronous, our backtraces are longer. Like even here we can see it. So they are like, I think it's like 3 screens like this one. Like this, then the same this screen, and another one screen on top. So they're really, really long. So we don't know where to look at, because this is our function, less than 20%. What else? What else? Another problem is that when we're using asynchronous times, it's not only about Tokyo. Other runtimes works the same way. So we don't know what is executed in which order. Everything is asynchronous. Here, there, this task, that task, we don't know anything about that. There are many threads in use. So we can analyze thread by thread. Or we can use one threaded version of Tokyo, of course, but then it will be not that performant. So we have issues with that. The good news is that if our program is fully asynchronous, things are getting a little bit better. So this is a asynchronous version of the same program. We have Tokyo main function, which is a macro which converts our main function, asynchronous main function, to some other main function which initialize Tokyo. And then almost the same function, but instead of, like we are doing await here. So we have 2 points of that asynchronous code. So we are waiting on request, and we are waiting on transforming to text. So if we run it, the result will be like this one. So visibly, half of the time, not 20%, but almost half of the time is taken with our function request async fetch there. And half of the time is by Tokyo runtime. So it's a little bit easier here, but still have half of the time, like someone is doing something for us. We don't know what's going on there. So when we are talking about profiling asynchronous programs, we have to think about this part. So how to find out what's going on. So one of ideas, and now I'm showing you how to work with one very small, very simple crate. I don't think that is meant to be used in production, but it's a very good, small step, but very good one. So we can diagnose futures. Like this await blocks, they work on futures. So this function, future diagnose, just add something to every future here. So we have future number 1, await, future number 2, await. And with this small crate, we can get very useful information. If we run this program, it will generate special profile.json file, which is a tracing file, which we can read with special tools, not tools from JetBrains. Just we can do that in Chrome, Google Chrome, and we can get something like this. So this is a visualization of that profile. And it's, when you look at those graphs, you always have problems with understanding what's going on. Like, there are a lot of graphs everywhere, so you have to think carefully about what's going on here. But here it's actually very simple. So these triangles here, they are like wakening our futures. So they are wakened at some point. And then if we change the scale of this picture, we'll see a lot of interesting stuff. So maybe here you can see this something like this. We have vertical lines and some horizontal lines. Those are actually these vertical lines shows polling. Polling is where we are doing await. So we are awaken, and then we run some code, but then we see if the result is ready, we process it. If the result is not ready, we go into sleep again. So that's the usual life cycle of a future in asynchronous programming. So our goal is to minimize those awakenings without actually doing job. So we check, sleep again, we check, sleep again, and then finally we get some result. So we want to minimize the number of those cycles. So if we look closely, we'll see something like this. So this is like the dependency of those pollings, so several pollings, and finally we get the result. So we get is ready. So we are ready to text. So this is one is about transforming to text. And we see that transforming to text never actually gives us several pollings. It's ready almost immediately. So in this program, for every get, in general, like in average, we get 3 pollings for 1 call. So it's easily visible from this graph. So what we're coming, so the idea may be, if we see that regularly we get those 3 empty pollings before actually getting results, we can tweak some parameters for Tokyo to make that period a little bit longer. So we can do something about that. But at least profiling is not about fixing stuff. It's about understanding what's going on. If we see that regularly we see those 3 polling without any result, well, that's a reason for slow performing. So basically, we have this paradigm shift. So we're going from sampling profilers to tracing. So this tracing is just changing the way how we profile. It's still profiling, and the file is called profile.json, but it's a little bit different. So I'm going closer to the conclusion. So when we are talking about profiling asynchronous applications, we know that this profiling becomes tracing in most cases. So we generate those traces, we analyze them, and of course we can look at flame graphs, but they are less informative in these situations. So tracing works better in this case. So one example of that generating and analyzing traces is futures that create small crate, futures diagnose. Just one example, very small. It focuses on the time of awakening and polling the futures in asynchronous code. And another example, which is much more important, is so-called Tokyo console utility, command line tool for looking at asynchronous applications. So an idea is to write some instructions for collecting data about how Tokyo performs. And then we display those data and explore data interactively. Like if you instrument your program, it generates the stream of events about Tokyo. And then you can get at runtime this utility with this view. So you can see Tokyo tasks. You can see some statistical information, total time of running, when it's busy, when it's idle. This, by the way, this example was provided by like documentation from Tokyo Console. And there is another mode when you go, so you can, it's interactive. You can go to any of these tasks and get additional information, some information about futures, like poll times, how many times you polled your request, stuff like that. One problem with this tool is that when you do that interactively at runtime, everything changes very quickly. You don't have time to analyze all that. Well, you were here and then everything changed. And you have no tasks at all at this time. So sometimes if it's very stable, you can do anything about it. Sometimes you can't do anything, unfortunately. So the better way, which is suggested at these cases, is actually to take those data, diagnostic data, and transmit them via like open telemetry stuff somewhere, like to some service which is able to collect those data. So we generate the same tracing information, but send it to some collector. It can be Honeycomb.io or Jaga, which is very popular in this area, Prometheus. Those are like services for collecting open telemetry data. And then you can process that data later. So you see all those polling times, awakening times, everything. So it's just a totally different way for profiling stuff because it's now asynchronous. And finally, so if you write some asynchronous applications, well, normally the load is unstable. Like if it's web application, it's like, so now you have a lot of load, next second you don't have any load at all. And in this case, it's not the best way to profile it because what you get, you don't know. So usually you combine it with some, so you run that code at some server machine. So you want to make it like look like real production and not just trying to do all this stuff like on your MacBook or something. So you have real server, you run it there, and you generate some load, better stable load. Like for example, I recommend to use Goose here. Goose Attack, it's a very nice tool which is implemented in Rust, which generates stable loads. And you can provide various scenarios like this authenticated user, unauthenticated user doing this and that. And then you get this nice reporting system for the time of every request. But at the same time, you can generate those traces. And you also can use IDE Profiler at that setup. So if you have some remote development tools, you can connect your IDE to some remote server, run Profiler, and then you get all the information. You have sampling Profiler on server with remote development. You have traces collected somewhere in that collector via open telemetry. And now you can get all the information about your stuff. So that's an idea. Yeah, and that's it. That's it for me. Thank you very much. Yeah. I don't know. Do we have time for? It looks like we are a little bit behind us.
You're always behind.
Okay, that's great to know. Yeah. So if you have any questions, I'm ready to answer.
I have a question about JetBrains.
Yes.
That's okay.
Yeah, absolutely.
Because I was wondering why you develop a Rust plugin, not using Rust Analyzer, as all others do. Still provide support for Rust Analyzer. And what would be the benefit of me not using AppCode or PyCharm with Rust plugin compared to CLine?
Okay. So we started working on IntelliJ Rust plugin, I think 6 or 7 years ago. There were no Rust analyzer at that time. First, the original developer, the first Rust plugin developer at JetBrains was Alexey Kladov, who later left JetBrains and started implementing Rust analyzer. So yeah, those are very interesting facts. Folks nowadays don't know that. So the main developer of our plugin left JetBrains and started Rust analyzer. Then these two projects, so JetBrains decided to continue work because we had users for our plugin, and it like Rust analyzer was not the best solution at that time, like many years ago. So JetBrains decided to continue development with other developers. And in fact, even now, we are very big friends with Rust analyzer team. We share some ideas. Like there are tools which were, like there is this macro expansion tool, which now is part of Rust-Up, which is installed on every machine with Rust-Up. It was developed at JetBrains, and it was a student project at JetBrains. But then ecosystem adopted it, and now Rust Analyzer use it to expand macro, and IntelliJ Rust plugin use it to expand macro too. So we in some sense we are competitors, of course, but in other sense we just work together to provide two sorts of different experiences. And if you know, we have Fleet, and Fleet, another IDE from JetBrains, actually supports Rust Analyzer. So if you use Fleet, there is a Rust Analyzer which is called from Fleet, so we support it too. So we always think that competition, healthy competition, and supporting each other is a good thing. So we don't want to close our product in favor of another product, because it doesn't make sense. They provide totally different experience. There are folks who use our products. Like according to research we do, we have like 30% of market share, and 55% is VS Code with Rust Analyzer. So it would be unfair to close the product which is used by 30% of Rust developers in this world. So we don't do that. And maybe we can do something different. So that's it. That's the answer. So we don't need to close it. It's quite a successful product, and it's a plugin. So the best way to use it is via CLion at this time. So in PyCharm we have limited version. It's for technical reasons, partly for technical reasons, partly for commercial reasons. And in IntelliJ IDEA is also a little bit, it's more powerful than in PyCharm, but still limited. So CLion provides full experience. Like Profiler works with CLion mainly, for example. Debugger works with IntelliJ IDEA and CLion, but I think it doesn't work with PyCharm. So there are some differences here. So yeah, that's an idea.
But the debugger is the same. I'm using AppCode. I don't know you discontinued it.
Yeah.
Using AppCode now for Rust development currently.
By the way, I didn't know that Rust was available in AppCode. So you still continue to use it?
Yes, I think it works.
Okay.
I have a subscription. It's running out.
Okay.
Fall, I think.
Yeah.
But it works.
Okay.
I was wondering if the debugger is a bit more clever in CLion.
No, it's not. Well, this debugger is actually a wrapper over GDB or LLDB, depending on what you use. So no, it's not more powerful. Yeah. We have some plans about debugger, but they are not ready yet to be shared. Yeah.
I'd love to see more. Like, if you have strings and some, you have a Rust type that is basically a string type def.
Mhm.
The Rust debugger doesn't display anything; it just displays pointers. Or you really have a hard time to see what the string actually contains. For example,
We were discussing precisely this problem today, like several hours ago. And I brought this topic because, well, when I compare debugging experience in VS Code and in Selenium with our debugger, you see that immediately, that difference. So you have to press a lot of buttons, a lot of presses in order to see actual stuff. So yeah, we'll definitely do something about that. That's for sure.
that's nice to hear.
Yeah. I promise you. I'll make it happen because I'm struggling with it too.
Do you already know how much it will be? How much it will cost?
No, nobody know. We don't have a solution right now. No, we don't know when it's going to be released, so we don't know the actual pricing model. Nothing. Yeah. I think, well, if you look at Fleet page, there are some information about, like, there is an idea to make it free, make it totally free for hobby, educational projects, for open source projects, but the actual pricing model, actual like numbers, we don't know yet. Yeah. Other questions? Yeah.
I'm kind of wondering if there will be some better thing, some more introspective view than open telemetry for profiling, because profiling is more than just thinking about how long something takes. It's about, do you block a thread? Do you do number crunching?
Right.
Is the thread just idling around, and so on? And I think for web development, it's very easy to use Tokyo tracing, for example. You can see, like, this function took 5 seconds and it idled around 4.99 seconds. That's mostly what you see tracing. But if you go like to, for example, game development, maybe you don't have an async runtime there, but you do async IO stuff all the time. And you have basically some parts where you need to block your thread and wait until an event and something like this. And I did use FlameGraph for this, and I also, it was really horrible to find out what the bottleneck is for this.
Yeah.
So I'm thinking about, is there, like, there needs to be some better protocol about this, like blocking threads and something like this. You actually don't want to have it if it's possible, or just block very shortly, I don't know. But if there is a better introspection than tracing, actually.
Yeah. Unfortunately, you are totally right. And as far as I know, there are no ways for doing that. And that's actually, I started with this. We don't have like enough users to apply some more efforts to that stuff. So of course it's a problem, and that's something that should be solved by the community, by the whole ecosystem, not just JetBrains. Because of course we rely on debuggers, we rely on tools from the ecosystem. So we are not able to do everything by ourselves. So yeah, you're right. So, and that's by the way, like if you compare with Go programming language, you can get all that information very easily. So they have everything ready for that kind of analysis. And we don't have that in Rust. Maybe you can do that like via perf. Maybe instruments is very powerful in macOS, for example. Sometimes they have so many views of your program. Maybe it's possible to find something there. But yeah, that's really complicated stuff. Yeah, I agree. And it sounds like something simple, but yeah, it's not there. Or maybe I'm not aware about that, but yeah, I know that that's a problem. Yeah.
Thank you.
So tracing is mainly for web application. It works just great. You're right. Yeah, but for other areas, but maybe what we see actually, we've done some surveys and we see that web development in Rust is growing. So, and we don't see that for other areas, by the way. So maybe folks from web development do something useful for others too. I don't know. You don't believe that, yeah? It looks like that. Or maybe, I don't know. Yeah.
Thank you.
Yeah.
Pizza
Yeah.
is here, so.
Okay. Thank you very much.
Willst du mal schauen? Ich höre mich zumindest. Ja. So. Kannst auch gerne mal Screen 2 versuchen oder sowas, wenn das einen Unterschied macht.
Müssen wir die Kamera einfach rüber drehen. Das ist so schön.
Ja, funktioniert? Okay, okay, dann sollte ich mich nicht vor die Kamera stellen, oder?
Ja, doch, so. Kannst du dich da hier so.
Was, hier so?
Ja, genau.
Dann schaue ich mal. Bisschen rüber. Okay, good to go. All right. So, hi everyone. My name is Oliver. I am a software security researcher, currently working at Fraunhofer ISEC, which is a research institute for cybersecurity in Garching. And I was looking into Rust like 4 or 5 years ago, and for my research group, we're at the Secure Operating Systems group, and we look at software security for low-level software, so the stuff that runs on top of the Linux kernel, for example. And I pretty much saw a lot of advantages with Rust for this type of software, and this is what motivated my research of going into it and seeing how we can do the transition from unsafe languages to safer languages like Rust for that domain, to make the world a little bit sort of a safer place. So yeah, today I'll talk to you about how to keep ensuring memory safety for this process of transitioning from C++ to Rust. So some advantages from my point of view, personal point of view, or maybe let me say that all of this is just my personal opinion, does not represent the opinion of my employer. Okay, so from my point of view, there are a lot of advantages in Rust, and first of all, just like all the things, it makes it fun programming again. So who of you here have been using Rust before? Okay. Who of you, like me, just have fun programming in Rust? Okay, a little bit less, but still a lot. I have another talk on more like this from a management perspective, but I want to focus more on this type, those arguments today, because those are the arguments that I've been using more when talking with companies about Rust and how to move there, and what it brings for the companies, because they have to have an argument to start using Rust. And one of the arguments that I bring is that the security by design part moves a lot of cost from fixing bugs after deployment towards more fixing bugs during development, during compilation. And Rust does a great job of supporting us with that, with the type system that enables memory safety and that erase-free programming for multi-threaded programming. And the trade system enables us to come up with a secure API design, which I think are great features of the Rust programming language. Today, we want to focus more on this memory safety aspect. So quick summary, maybe. Who of you is familiar with the terms of memory safety itself? Okay, a lot. That's great. I can skip over that pretty quick. Those are two definitions of spatial and temporal memory safety from academia. So essentially, spatial memory safety means that whenever a pointer accesses, or whenever a pointer is dereferenced to access an object, spatial memory safety means that it will be ensured that the pointer will only access the object within its bounds. So you have no out-of-bounds vulnerabilities and stuff like that. And temporal safety just means like whenever you dereference a pointer, the object behind it is valid. So it has been allocated and has not been freed so far. So you eliminate bugs like use after free. And essentially, and this is the great thing for me, like the Rust type system enables us to have this and eliminates this whole class of vulnerabilities, which makes it possible for attackers to
exceed the boundaries. Exceed the boundaries of
yes, and by that, like override instruction pointers and hack into your program, essentially, like take over the control flow of your program. So this is very essential. But with all those advantages that we have in Rust, there's this movement of a lot of people who are excited about Rust that say like, just rewrite it, just rewrite everything. But as we see so far, it's not that easy. Mainly because we have problems on an organizational level. So if a company decides to take a look into Rust and evaluate it, they will come up with a lot of points where there will be costs. So rewriting a complex piece of software that you've already written like years ago, it's very complex and tedious, very costly. You have to train your existing employees, your developers. You maybe have to hire new developers because like maybe you have some older guys who do not want to switch from C to Rust or something. And you have to adapt all your development and test processes. So it's not that easy. So my prediction, and we see this, is that in order to get to a point where you introduce Rust into your company, you have to do it step by step. So very, very gradually. And this might mean like if you have a software architecture that's distributed like client server software, you can start with leaving the server as it is and just like porting the client to Rust. Right? Awesome, very self-contained. Straightforward if it's small code base. But if you come to systems level programming, you have monolithic binaries. So just one binary that runs it all on one system. And what you will have to do there is you have to assess the code base and assess those like strongly connected components of code, functions, self-contained code modules that you can easily refactor and replace by Rust code. And this would be like the process that I would imagine. It's like you identify those parts, you rewrite them, like very small code, start small, and then you test them and you validate that the behavior of your new code, of your new Rust code, is the same as the old C++ code before. And you as a company, as a team, you have to evaluate how this process was, if it brings you any benefits, and if it's good, then you repeat this over and over again. But in the middle of it, what it leads to is like you will have some mixed language binaries where you have C and Rust code within the same address space. If we continue this like forever, maybe at some point all of it will be Rust code. But for a very long time, probably we will stay in this part. And having those mixed language binaries is powered by Rust's foreign function interface. Who of you has ever worked with foreign function interface yet? Okay, that's good. Also, other question: who of you has tried to encourage their manager or whatever or team to move towards Rust and was not successful? Okay, some. So maybe this gives you like a little bit of an argument. If you're interested, talking more about this, or like talking about like how to maybe encourage your manager or whatever, please reach out. It's very interesting for me, this topic. So back to Rust foreign function interface. What it essentially is it gives us the possibility to have direct function calls between Rust code and C code. So how it looks like in the end would be you have your old legacy code, and you have like the things that you want to replace, and you have to write like a small portion of unsafe Rust code, this interface code that will do the calls in and out. And you will have safe wrapper functions that wrap those unsafe code and check like conditions so that you can safely call those C code. And basically both files or both set of files are compiled with their compiler. Maybe, for example, Clang on this side and obviously Rust on this side. And then you have your library, they get linked together, and you have like one executable program where C and C++ run in the same address space. But because of that, you have a problem, because mistakes that will be made in this unsafe part, either here or even more importantly here, they can translate into your safe Rust code and just fuck everything up. Sorry for my French. It actually, there's some research papers showing that there will be problems here because people make mistakes of writing safe interface, correct interface functions. So for example, what can happen is like you can have a Rust vector here, you take a pointer of it, transfer it to C, and C it will be freed, and then the execution will come back to Rust code. The object still exists in Rust code, and then it will be dropped automatically by Rust, and you have a double free vulnerability. So this is just an example of what can happen. And one of the solutions that I'm researching in is using memory safety sanitizers to solve this, to essentially insert additional security checks in those unsafe code parts that guarantee the memory safety. And then in the end, this is what I hope to come at, or this actually works. You have a program which is completely memory safe. So exactly, this is the goal, having a mixed language binary where you can come from C++ to Rust. You have both languages in there, but it is still completely memory safe. And compiler-based memory safety tools, this is what I'm specializing in. These are very easily for developers. You just activate them by a compiler flag if no source code changes, and it detects all those memory safety violations we just talked about. The whole negative side of things is the runtime and memory overheads that will be introduced by those additional security checks. There are two implementations of memory safety sanitizers in LLVM, which is Address Sanitizer and HVASAN. Who of you is familiar with the LLVM compiler framework? What it does? Great. Then let's see. This is how you can use it in Rust. So if you compile your binary with cargo, then this is the things that you can use to do this. if you compile if you compile it via C++ build tools, there are other ways described here how you can integrate it, I think. But yeah, I think we could like use a little demo here, and this is what I brought. I hope it works. This is my work environment. If you see those references to something called SafeFFI, this is the working title of what I'm researching on my prototype. What we see here is an example of an out-of-bounds access. So we have a static array here with 4 elements, and we convert this array to a raw pointer in Rust. It's not really, you cannot see it here with the types, unfortunately. Maybe I should use CLion IDE or something. But yeah, if we add a high number here, this will cause, like, we increment the pointer by 10, and then we dereference the pointer, so this will access this area out of bounds. Let's see what happens here.
I think there's something that you have to comment out. Line 4.
Yeah, good point. We do this. This is just to show that it works both with statically allocated objects and dynamically allocated objects. So I hope that this works. So this is the thing that we use, which most of it is uninteresting for you, but we use -C sanitizer Harvey address. You can choose from a lot of different sanitizers here. I can explain later why we like to use this. And then we link all of this together with LLD, the LLVM linker. This is something I wanted to tell you about later. And you have to append the target because otherwise the build scripts will be built with this too, and this is not what we want. So let me delete this. And just to show you here, so it will go really quick. This is the compilation, and now we can run this, and we see the output of the sanitizer. I'll try to make it a little bigger. So it gives us tag mismatch on this address. I am not trained in reading this right now, but I think good developers will be able to. You can symbolize this and get like really Rust function names and stuff out of this. But it shows you where you accessed memory that was out of bounds. What you have to do if you are not presenting this but doing this like really doing this is, give me a second. Oh, I'll do it here. It's easier. You have to append this z build std, which makes it build the standard library, so that the standard library itself will be instrumented with those additional security checks. So my example just worked because there was no issue in the standard library at that point, but you would want to need it. Let's see. Okay, so some of you might have already come to this thought. Sorry, can you ask me again?
Does it also detect like accesses to uninitialized memory?
I'm actually not 100% sure. Might be not the case, but there's actually another sanitizer for uninitialized memory you can use with Rust. But I'm like more concerned about the out of bounds accesses and stuff like that. So some of you might already come to the thought like, if I activate those memory safety sanitizers for Rust, like all of this code gets instrumented with additional security checks. Why do we need this? Like Rust already like provides memory safety for us. And that's correct. So my core goal with the research prototype that I'm working on is like, I only want to instrument the C and C++ code and the unsafe Rust code. And for all other Rust objects in safe Rust code where the Rust compiler can already guarantee me memory safety, I just want to omit instrumentation and save a lot of instructions, time and memory. So simple example here is you have a little small program and only B gets converted to a raw pointer, and this foreign function is called with it. So that means that we have to instrument additional security checks for B, but A will be fine. This is a small example of what we will do. And what we found out is that the primary way of exchanging non-primitive data types is by converting all the Rust structures to raw pointers, because they have an easy data layout that makes it easy to put them into FFI, and essentially they have the same layout as C pointers, and so it's easy to use pointers to transmit the data or call functions on this data. And these are all the Rust types which I call safe Rust pointers. They are all represented internally by pointers in machine code or in LLVM IR code. Your references, arrays, slices, and when they get converted to raw pointers, this is where we want to jump in and let the memory safety sanitizer earn its money. It comes down to this thing. During compilation, whenever we convert a safe Rust pointer to a raw pointer or vice versa, we want to keep track of the spatial and temporal memory safety properties. So if we have an array of size 10, and at some point we leave the Rust safe space, convert it to a raw pointer, because of the Rust strong type system, we know the size of this object, and we can emit this into LLVM IR code, and the memory safety sanitizer can use this information and can start inserting additional instructions for safety there. And the same thing back. So if we get a raw pointer and we want to convert it to, let's say, a reference to a Rust object, then we already know, because of the Rust object, because of the Rust type system, what size this object will have, what size the struct will have, and we can emit an expected size. So we can say, whenever we convert raw to safe, we want the memory safety sanitizer to assert that the object behind this pointer is at least this size big. This is the core of what I tried to come up with. And this right here is the architecture that I used for implementation. So you have your Rust source code here, bring it into Rust C, and within this, it will be lowered into different intermediate representations. Who has heard about all the intermediate representations in the Rust compiler? Okay, not all of you. I just like quick overview. Abstract syntax tree is just like a data structure for representing the syntax of the source code. It then gets lowered to the high level intermediate representation. It gets desugared, so desugaring loops, desugaring like async functions and stuff like that. And at some point it gets type checked, and I'm not 100% sure what happens here. But eventually it gets lowered to the mid-level intermediate representation. And this is a representation that is awesome for doing analysis, program analysis, because it still has all the type information of from the all the type information about the Rust objects, but it's like low level enough, simple enough that you can do like easy analysis on this. And this is where we implemented our safe FFI modifications of the Rust compiler. So we do exactly what I said here. Like we traverse all the source code of every function, and whenever we see a conversion between safe pointer and raw pointer, we emit those expectations or those sizes that we want. And this will be done by emitting LLVM metadata nodes on every LLVM instruction that corresponds to this conversion instruction. So and at this point, we get an LLVM IR file, and we pipe it into LLVM and activate our safe FFI LLVM pass. It catches all those metadata nodes. So you have to imagine those metadata nodes. They will be emitted on every conversion instruction, but every instruction after that uses this converted pointer, that has to be instrumented too. And this is what this pass does. It does a intra-procedural forward data flow analysis and checks every use of this raw pointer, of this unsafe pointer, and instruments it with or tags it for memory safety checks. And then we have potentially multiple sanitizers, and you can choose from one, whichever properties you like best, and they can query the safe FFI pass and ask, hey, is this pointer safe or is it not safe? Should I instrument it or not? And then it gets, like, you get instrumented LLVM IR, and in the end, everything will be memory safe. We we did tests with 2 sanitizers already, HV-ASAN and softbound CETS, which this one is maintained and known by a lot of people. This one is actually a research prototype from 2010, which was originally written for LLVM 3, and we ported it to LLVM 9 and now to LLVM 12. And it's a little bit of a mess, but its promises in theory are that it's very precise. So you can very precisely check for the bounds. HV-ASAN has some disadvantages in precision, but it has some great advantages for speed and especially memory overhead, because it uses some hardware features from the ARM architecture. But we can talk about that later if this is of interest for you. So just to give some preliminary results, we have to do like a lot of more tests, but what I can show is like, what we can see is like, scratch this away, Rust standard library. We did like one test where we showed for a safe Rust binary, like fully safe Rust code, which of course has its dependencies, especially in the standard library where unsafe code is used a lot. We can omit like 86% of the instrumented instructions. Of course, that does not translate directly to performance, because performance is dependent on what the application does, the profile, like how often does it access memory, how often does it use like integer floating point operations and stuff like that. And we tested it with a program that does those Leeton-Mikali signatures, which does like no I/O and a lot of memory object manipulations, which is the worst case for those memory safety sanitizers. And those are the results so far. So this is what it runs without sanitization. This is with HV-ASAN, and this is with our optimizations, which looks like we did a great job of making it faster. And security, our security tests so far, we tested 9 known vulnerabilities, CVEs of these crates, and 8 of 9 are detected with HV-ASAN. Not sure about the one that it's missing, But the great result for me is this, like everything that can be detected by Harvey Asan can also be detected by our SafeFFI prototype, but with better performance. This is what we aim for. One limitation that we definitely will have is transmute call, which is a extremely unsafe function that will convert like whatever bit blob you will give it to whatever object you want. And this is hard to reason about. So you can just give it a bit stream and convert it in a vector with its own like size metadata and stuff. There can be a lot of fuck ups. Yeah. And this is our outlook. So what I want to do next is optimize our SafeFFI LLVM path to recognize more safe pointers, to do more optimization, less checks, better performance. And I want to do more tests with real-world software where Rust and C are integrated into each other, like Chromium and Firefox. And if you happen to have some kind of program where you're working at that has this mixed languages, please reach out. I would be happy to run some tests. Even better if you already had vulnerabilities in the past, and you can we can reproduce them, see if our sanitizer can fix them. That would be great. And then in the long term, implement those optimizations for more sanitizers. There are some more research prototypes out there. There's also, I don't know if you heard of it, a new architecture that is developed by University of Cambridge, and I think Huawei is part of it. They are called Cherry, and they do memory safety in hardware, makes it extremely fast, and they are also working on optimizations for Rust. And then, yeah, a great goal would be extend this concept to more programming languages that are based on LLVM, so we can have those benefits for other programming languages as well. So I tried to come up with some main takeaways, because you probably are not all compiler developers, but maybe what you can take with you is that if you want to encourage your development teams or your managers to start using Rust, do it step by step. Start small and extend from there. And use this FFI feature. And if you can afford some computational overhead right now, use your sanitizers for C++ or unsafe Rust code, whatever you have. You have GUI software where you have to wait for user input, easy, like this 2 to 3 times computational overhead, it will not show. Or anything that's IO heavy where you have to wait for IO, all this effort will go down as compared to network overhead. Yeah. And unfortunately, this is not available on stable Rust right now, but only on nightly. And I think that's it. These are my contact information. So as I said, please reach out. And I am also at the point in my career where I want to take the next step and commit more of my work towards bringing Rust in the world. So if your company is interested in that, or has problems with that, or want to talk about how can we approach getting to Rust, please reach out. We'll be happy. Thank you. Yeah.
Basically, in order for the sanitizers to work, if you allocate objects, the sanitizer needs to know this object. It's this address, it has this size, right? What data type? So I remember there was an API for that from the sanitizers, and this means basically any object creation also which gets created and can potentially be passed to unsafe code. Basically, you naively need to call this API or make it known to the sanitizer, or you have some kind of, tracing. Oh, this object is created here, but it will never go into an FFI call, and so I can avoid basically making it known to the sanitizer, because that's still safe code that's created, right? So
Yeah.
And it has overhead.
Yes, but the approach that you just described of like tracking the flow of an object and see if it ever gets called into Rust code, this is something that I tried earlier, but it turned out to not work that well because static analysis is like it has its limits of precision and speed. So this is why we came up with this idea of that raw pointers are this one point where the safe world and the unsafe world get converted into each other. And if you ensure at this point that memory safety guarantees are intact, then it will be intact for the whole program. So that we did this way we can omit the static data flow analysis.
And also says, but you make every object which gets created known to the analyzer.
Actually not. So this enables us to not do this for every allocation, but just at the point of conversion, because usually when you would like to check the bounds of an object, you would need the sanitizer to know the size, as you just mentioned. But since we do not instrument every allocation for a safe object, we do not have this information at the sanitizer, but we can inject it at the point of pointer conversion, because the Rust compiler gives you access to the type information every time. So for the whole program.
Basically, right? You can test some object which has been allocated twice to unsafe code, and then you need to know basically you need to track it, or maybe it doesn't hurt if you make it twice.
Yeah.
What happens if I write my own allocator, use Russian alloc or mmap on somewhere to get memory? Probably this will not be traced, right?
This is something I haven't experimented with so far. So custom allocators might be a problem for this. I think as long as you use the Rust, what's it called, like __ Rust alloc API, then it might work, but I'm not 100% sure. There was another question.
Suppose I have a slice, right? Slice of integers is just a pointer to an integer and an end, and I can just put this on the heap.
Mm-hmm.
And then I pass a reference of this to C, get the file.
Yes.
C can then modify, for example, the length attribute, like the length field of this tract, right? Such that when in Rust code I try to do a bounds check, the bounds check might say, yeah, you're good. You are in bounds, but you're actually maybe out of bounds of the allocation the pointer is pointing to, right? So when I have a slice and I convert it to a pointer to pass it to C, which I don't have to do, but like suppose I convert it to a pointer and I pass it to C. Where do we track or store what was the actual original length of that allocator? So that and how do we find out later on when we come back from C? Like what was the address, what was the original length, did C mess with us?
That's a very good question. Let me see how to answer that. So the original hope is that whenever you pass a pointer to slice to C, C only has this pointer, and you would have to derive a pointer, or you have to, I don't have any graphics, but only based on the address of this pointer, you know where the length field is, right? Because it's probably right next to it. But you can only, you cannot access the length field via the pointer because it is behind the object, behind the allocated buffer of the slice. So with the pointer towards the buffer of the slice, you cannot access the length of the slice.
Okay, you limit the memory space that C can control.
You limit the memory space that C can control through this one pointer.
So you cannot
Let's say you want to.
This is an argument.
Why the safety pointer is stored at the wrong location. It's stored at
If I pass a slice to see,
Yeah.
that's I can pass actually a reference to a slice to see. Right?
Yes. And
then C might want to use that slice. Might want to have like a struct type,
Yeah.
as a pointer and a length, and might to read an element of the slice, and maybe wants to do a bounce check.
Well, this is a custom problem then.
Before the pointer from this file for passing the pointer to the slice.
so what the thing is, if you pass a slice to C, you never pass the slice data structure itself. You only pass the pointer towards the slice buffer, and you pass an integer containing its length, but it will not be the integer that is part of the slice. It will be a copy of that.
I can put that slice on the
Yeah.
and I can then pass C a pointer to that slice.
Yes.
And that object has two fields. Right? It has the pointer field and the length field. So C can actually access it in parts. Right?
Yeah, but you would not. You could do that. That would probably cause a problem. But you can. Yeah, you.
With enough malicious intent, you could just in your function gets called, takes the address of the stack pointer and run and go and do everything on the stack, modify it, right? And maybe not these days because of stack protection, but you know where your caller is, there's stack frame of your caller is, right? And you could already modify it if you mean, but that's not its intended. Basically, maybe it's not intended to push this kind of stuff.
I think there are no guarantees that this is the case, so you need to use the into parts APIs of those objects. And the into parts, that you get a pointer and the length, so you can create a fat pointer in the C part.
Mm-hmm.
But there is no guarantee that the size is before the pointer. It is actually 100% every time, but maybe it changes somewhere in the future.
Yeah.
But even if you do that, right? Even if you say, I'm going to have a slice and you split it into parts, and then give C a pointer and a length. And then C gives you sometime later back a pointer and a length, and you do a from parts and construct your own slice.
Mm-hmm.
How do you know like that length is actually equal to the location that's behind the pointer C gives you? Like that pointer came from Rust, like you went to C and came back.
Okay.
How do you?
Yeah, I'm not 100% sure if I can answer that correctly, but what we do upon conversion back to a slice is we know the length. We should know the length of the slice at some point, and then we can emit those expectations, and then we would have to check this integer, this length integer, if it's actually between like in between the bounds of the allocated buffer pointer buffer object.
Like I can imagine that if you are going back to when you're going to C and you have a slice and you split it, if you have a global hash table somewhere where you have for this address I have a length, and you store it there, and then when you come back from C, you check that pointer in the hash table again, and then you can do some type of checking, right? Like I think about the LVMIR metadata points, right? Like those are kind of for like the struct object sizes, right? Like not for like dynamic allocations, they kind of point to everything.
Yeah, this is a very advanced question. Thank you for asking. I don't know really at the point. There might be like bugs with it, that this concept might be incomplete. This is like up to research. But if you would be able to, I would appreciate if you can write like a small proof of concept, send it to me. I can test it. That would be great. So knowing the limitations would be great, because every time you write some kind of static analysis tool or tool that enhances security, you need to know the limitations, and in the best case you already have some kind of pre-analyzer that checks your code if those limitations are there. So if I would have the transmute call as a limitation, it would be great of having a pre-analyzer pass that looks, is this transmute call there? And if it is, I just like tell everyone, hey, this security tool might not work with your program. But so it would be great knowing the limitations. Oh, sorry. He had this question first.
So the stupid question, are you suggesting to run sanitizers in production, or is it to speed up tests?
Good question. So sanitizers are usually used for fuzzing, so that memory access issues come up earlier when you fuzz something. But yeah, I actually intend on putting this into production, at least for those types of code where you can use it, like IO heavy code and GUIs. I have coded some GUI application for American football, and this runs on the address sanitizer the whole time, and it just works. It doesn't really appear to the user that it's slow. Good question.
Wondering what if the pointer escapes, because right here you pass a pointer, you expect to check it after the function returns, but the function, the C function, could store it in a global table or so and modify it much later at some totally unexpected point in time.
Yeah, that's a valid point, but this would be an issue of temporal memory safety, right? So I did not fully implement temporal memory safety yet, but what I will try to do is come up with a solution that as soon as a pointer gets converted into a safe Rust type, we will mark this pointer as it is still alive, but you may not be allowed to free it because it will be automatically freed by Rust during drop. So that way, a pointer to that object that will be used later in C code might not allow is not allowed to free this thing, and still because of those additional checks in there, it can only access it within its bounds. So that should work theoretically, research-wise.
Just a question for my understanding. So this additional save FI that you have implemented, is this now like happening in LLVM? Is this like C++ code that you have written, or is it already happening after the mere representation is produced?
Yeah, it's actually both. So it's two parts. It's here where I have a modification of a Rust compiler. I do have my own Rust compiler essentially, which traverses this MIR code and emits those type information. Because you actually lose a lot of type information during lowering from MIR to LLVMIR. So yeah, this is one part is here, and then one part is here in the sanitizer where it collects those additional type information and does the instrumentation.
And you have written this part in LLVM in Rust to be able to be part of LLVM through FFI then, or is it C++?
No, it's C++. Okay. This is C++ code and this is Rust code.
Right.
No. Yeah.
Can I read the kernel?
Sorry, can you repeat the question?
Can I build a kernel?
A kernel? I don't know. I know that there is extensions to the address sanitizers in LLVM for kernel building. So you have the a kernel address sanitizer, but I never used my approach with this. So might be interesting for what's the Rust kernel that's being developed? That's too many. Yeah, but yeah, might be interesting. But I haven't used sanitizers for kernels yet. I think that the Android project is using this at some point for their kernel. Yeah, essentially. I think there was some effort at some point to make the Clang compiler be able to compile the Linux kernel so they can use the sanitizers for that.
I don't know if you mentioned, but is it runtime or compile time checks?
From the sanitizer?
Yeah, it's runtime. Right?
It's runtime checks, yeah. That's why it blows up the performance.
Do you have any idea or approach to maybe you can put it to compile time at some point, like just analyzing the assembly and say like there is some strange things happening here?
He actually analyzing compile time, where are the dangerous parts, to check at runtime only the dangerous parts, right?
Yeah, that's correct.
Exactly the point.
That's correct. But it's a good question. You can either even go beyond that. I do have a colleague who's researching on doing this not with Rust, but with C and C++ code, where everything's unsafe, and he has some static analysis optimizations that can optimize out some security checks too.
Yeah, but the effects of those will be appears on the runtime.
Sorry?
The effects of those will be appears on the runtime.
Yeah.
I mean, the extra instructions will work on the runtime. That's true. He's just combining a new output, right? With this safe file.
New output?
Yeah, like a new output of the code itself. Without them, there's some instruction missing, which are the safe instructions.
Mm-hmm.
Yeah, so this is what I mean.
Yeah.
We are adding extra instructions.
Yes.
This is what called the runtime checks. It's what calls like use or like overhead.
Yeah, exactly. So you get a different binary, and this is the overheads that you will see because of the different binary.
So it's runtime. It's runtime check.
Yeah, it's runtime checks.
To the point that sanitizer checks everything at runtime. He checks at compile time which parts we can skip runtime overhead for.
Yeah, but the instructions runs on runtime. This one.
Mm-hmm.
Yeah, but not for
Yeah, you're both right.
Yeah, not for.
And that's why we can. Yes.
Yeah, it's sometimes easy or difficult to show it because like parts of it is during compile time, parts of it is during runtime. So this comes up often. Yeah. But yeah, guys, these were great questions. Thank you so much. Thank you for your attention.
Thank you.
Yeah. Thanks for having me here.